Okay, our final mode of detection in GC, the final one we're going to talk about anyways, is mass spec. Mass spec detection for GC. And I would wager that this is probably the most common thing now. People generally it just rolls off the tongue now is GCMS. People don't even really talk about just GC anymore. It's because it's easy to package these things together as a single instrument. They take up essentially no extra room if you put a nice compact quadrupole mass spec on a GC. And I'm not going to get too deep into mass spec here, as fun as I think it is, but there is this really nice complementary thing, which is that it's easy to do mass spec on molecules that are light. And GC necessarily works on molecules that are not that heavy. Once they get too heavy to be volatile, they can't go by GC anymore. And so this makes GC and mass spec such a beautiful pairing. Um, there are, so as we talked about NLC, we said the thing that we're going to tackle is the ionization method. Everything that comes downstream of ionization, you can learn about in the mass spec course with Dr. Doe, and I highly recommend it. It's much better than the old mass spec course with Dr. Baker. Um, so go there to learn about your mass spec, to learn about things that we've talked about with other detectors, like linear ranges and limits of detection. We're not going to talk about that here. What I want to show you is the instrumentation we need to make the coupling of GC and mass spec happen together. And so we're going to stop at the ionization method because that's the first step in mass spec, and that's where GC interfaces. So there are two main, they're not the only ones, but there's two main ionization methods for GC MS, and they are electron impact ionization, which is abbreviated EI, and chemical ionization. So I'm going to show you how, so EI and CI. I'm going to show you how EI is done, how the instrumentation works for electron impact ionization. We're not going to talk about chemical ionization. It's a in-depth mass spec topic to talk about. But the one thing I will tell you that is pertinent here is that the instrumentation we use for both of these, the ionization source, is very similar. In fact, typically what you're doing is you're modifying an electron impact source to do chemical ionization. And that's as much as I'll say about chemical ionization. That source, which we'll see in just 1 second, requires your analyte to be gas phase. So both of these ionization techniques are gas phase techniques, unlike something like electrospray ionization where you're ionizing directly from a solution phase or a liquid phase. So both are gas phase, and that's a good thing, check mark. Right? They're both gas phase. That's good for GC. Everything coming out of a GC column is gas phase. But they are also both vacuum, or more appropriately, very low pressure environment techniques. They're techniques done under a high vacuum. And if you think about this from a GC perspective, lots of carrier gas flow, lots of high pressure gases, that's actually a bad thing. It's really hard to be at a low vacuum pressure when you have a high rate of flow. So we're gonna take a look at a couple of things here. First, let's look at the EI source. So electron impact source is a fairly simple thing. You have neutral molecules. Let's draw these as an N. So these things cannot be analyzed by mass spec because they have no charge. And this we'll assume is all coming from our GC column. So as molecules come off our column and they're neutrals, they're going to enter this environment of the electron impact source. The electron impact source is really straightforward. It's an a resistive heater, and it is an electrode plus voltage. And what this does is when you when you drive current through a resistive heater under a vacuum, you produce actually, kind of interestingly, you produce a rain of electrons. Electrons start firing off of this thing. It basically has to do with auto-ionization of the material as it gets hot, but the bottom line is you heat up this resistive element and electrons fire out of there. As your neutrals pass through here, there are these impacts, right? So hence the name electron impact ionization. There are impacts between electrons and neutrals. So as this electron is being accelerated towards that electrode, it will smash into this neutral. That will eject an additional electron, right? It'll knock an electron out of the neutral, and what you get out of this is a cation. So there you go. That ion can now be accelerated to the mass spec source. So yeah, here we go. So the one thing I want you to know and to think about here that we don't think a lot about in chromatography is that if you want these high energy particles to be able to just kind of travel through space, you have to take everything out of their way, right? The only thing they can crash into needs to be your analyte or your carrier gas, I guess, and not a bunch of atmosphere. So this whole thing is done at low pressure. You pump out all of the atmosphere that's in the way. And when we say low pressure, we actually mean like really pretty low pressure. So this is like micro torr, 10 to the negative 6 torr. I'll remind you, it's 760 torr to 1 atmosphere. So we're talking about 8 orders of magnitude lower in pressure than our atmospheric pressure. So the challenge here, the thing that we're gonna address through instrumentation is that if you send a GC flow rate, that would be a volumetric flow rate, Q, is going to be on the order of kind of mils per minute, right, or more. So you have a bunch of material that's mostly carrier gas that you're trying to dump into this low pressure environment. And the bottom line is, if you send all this in there, you can't keep low pressure. You will, all the space you've evacuated from atmosphere, you will fill up with carrier gas. So you can't keep low pressure when you're pumping at those kinds of rates into the ionization source. There is a brilliant solution to this. So the brilliant solution to this is something called a jet separator. So the jet separator works at atmospheric pressure. I want you to imagine you have flow coming off of, this is your GC column. All right, so this is flow coming from the column. And if you just stick that column out in into the atmosphere, right? Let's make sure that we're clear about this. This is atmospheric pressure. What's going to happen is flow that was flowing in a straight line down the column is going to suddenly explode in all directions out. Right? It's just like spraying air through a gas hose, right? It's just going to go in all directions. So this is actually a jet. That's what this is called. But the trick is that the gas expansion velocity in a jet is inversely proportional to molecular weight. When something is lighter, it expands into this velocity much faster. In other words, what you end up with is in the outer fans here, all of this stuff that we're drawing as arrows over here, going out, expanding out really fast. All of this stuff is carrier gas. It is typically much lighter in molecular weight, and so it expands faster out into the jet. Then the analytes, we're going to draw the analytes as these little circles, right? These little particles. These are going to expand too. They absolutely are. I mean, it's just natural. They're no longer confined by this. They're going to expand, but they're going to expand slower. And that means that if you carefully position now the inlet to your EI source, which over here is down at low pressure, but back here at the inlet, it's at atmospheric pressure. It's not like you're going to reject all carrier gas, right? Some of it's going to get in there, but you're going to selectively sample from a region that is more sample, heavier molecular weight than carrier gas, right? So this thing selectively samples analyte over carrier gas. And that works because the molecular weight of analyte is always going to be a lot bigger than the molecular weight of carrier gas. So it's going to stay close to the center. You're going to position the inlet to your EI source near the center of this jet, and you're going to selectively capture analyte. Okay, I think that's everything we have to say about hooking up a GC to one of these EI or CI sources. If you want to know more about mass spec as a detection mode, I highly recommend taking CHEM 513 with Dr. Doe. That's where we'll stop today. When we come back on Monday, we will talk about electrophoresis, my favorite topic.